Block diagram of PLL. PLL is nothing but phase locked loop. PLL consists of 4 blocks. First is phase detector, and the other one is low pass filter, third one is error amplifier, and the last but not the least is fourth one is VCO. The phase detector compares the input frequency with feedback frequency and produces the output, which is nothing but the function of phase difference between the two input signals, and the output of the phase detector is a DC voltage which will be applied as an input of low pass filter. Low pass filter removes the higher frequency components present on that DC voltage. Now output of the low pass filter is nothing but removing the high frequency components present at the output of error voltage or control voltage, which will be applied as an input of VCO, which is nothing but voltage controlled oscillator. Voltage controlled oscillator is an oscillator circuit which produces the output frequency depend upon the applied input voltage, and VCO maintains linear relationship between the applied input voltage and output frequency, and that applied input voltage is also called as error voltage or control voltage also, and VCO is also called as voltage to frequency converter. Now whenever there will be no control voltage applied at the input of VCO, then it will be operated in the free running oscillator, and whose output frequency is nothing but F0, which is also called as center frequency. And whenever you are applying a non-zero control voltage at the input of VCO, now that non-zero control voltage pushes the center frequency from F0 to F, which is nothing but F is equal to F0 plus kV into Vc, and we all know that F0 is nothing but the center frequency and kV is nothing but the voltage to frequency conversion factor, and Vc is nothing but the control voltage or error voltage, and the error voltage or control voltage pushes the VCO to produce the output voltage, which reduces the difference between the input signal and output of VCO frequency, and it will always try to reduce the difference between the input signal and the output of VCO, and this process is known as capturing, and it will be continued until the PLL is locked. Once it is locked, then what happened? Then the phase detector produces the constant DC voltage, and that DC voltage will be applied as an input of VCO. Then it will be treated as the control voltage, which is used to shift the center frequency from F0 to input frequency Fs. Operation of PLL, that is phase locked loop. And listen carefully, the PLL is operated in 3 modes. One is free running mode, and the second one is capture mode, and the third one is lock mode. In these 3 modes the PLL is operated. So I already told you that the free running mode, whenever the control input voltage of the VCO is equal to 0, then it will be operated in the free running mode. And listen carefully, in this PLL we have to remember 3 important definitions. What are they? First one is lock range, and the second one is capture range, and the last but not the least, third one is pull in time. These 3 definitions are very important to understand the operation of PLL. Tell me, what is lock range? Coming to the lock range, whenever the PLL is locked, then it can track the changes in the input signal frequency and the range of frequencies over which the PLL can maintain lock is called as lock range. Okay, and next coming to the definition of capture range, the range of frequencies over which the PLL is acquire lock is called as capture range. Pull-in time. Pull-in time is nothing but the capture range of frequencies is not produced as soon as whenever you are applying the input signal. When it will take some finite amount of the time to capture the input signal frequencies with the feedback signal frequencies, and the total time required to lock the PLL is called as pull-in time, which is nothing but block diagram of PLL. Here you have mainly concentrate on these three things, and one is very important formula, F is equal to F naught plus KV into Vc. That is, whenever you applied a non-zero control voltage at the input of VCO, immediately it will be shift the output frequency from the center frequency F naught to F naught plus KV into Vc. Then once the PLL is locked, then what happened? The phase detector produces the constant DC voltage, and which is used to shift the center frequency from F0 to input frequency Fs. PLL can be available in IC form also. IC 565 is used as a phase locked loop, and all the ICs are available in IC package types. Those are metal can package, dual inline package, flat package. Here this PLL is available in two forms. One is metal can package and the other one is dual inline package. While the PLL is used in the metal can package, it will be used as a 10 pin IC. While it will be used in the dual inline package, then we will be used it as a 14 pin IC. Now here it is a 14 pin IC. Now I am going to explain each and every pin in detail, and all these pins are also available in this case also. Okay, now listen carefully. Supply voltages are required to operate any IC, that is plus VCC and minus VE. So here it is minus VCC and plus VCC. To operate any IC, we require the supply voltages. Okay, next, the phase detector in the PLL block requires two inputs. Those are the two are direct inputs, and the other one is nothing but the feedback input, which is coming from the output of VCO, and the two direct inputs are applied at input number 2 and input number 3. And see this fifth one, phase comparator VCO output, that will be applied as another input of the phase detector. That phase detector compares these input frequencies and generates output, which is nothing but the function of phase difference between the input signals. And next, coming to the fourth pin is nothing but VCO output, then will be connected to the fifth pin whenever you want to use it as a PLL. Next, sixth one is nothing but the reference output for the op amp amplifier, which is nothing but the op amp also. And seventh pin is voltage control, VCO control voltage, which will be applied as an input of the VCO. According to that control voltage, VCO will produce as the output frequency. That's why the seventh pin will be used as an input pin for the VCO. And next, coming to the timing capacitor and timing resistors. These timing capacitors and timing resistors are used to calculate the center frequency of the PLL. while you are going to calculate the center frequency of the PLL, you have to calculate with the help of VCO. That's why we are applying the timing resistors and the timing capacitors as an input, and these 4 pins are not used. That's why here I am representing no connection. While you are using it as a dual inline package, you have to use it like this. And now this one will be representing the metal can package, and whatever the pin, these 10 pins which I explained for the dual inline package, all are also available in the metal can package also. Diagram of IC 565 PLL. This block diagram consists of phase detector, amplifier, low pass filter and VCO. If you clearly observe this block diagram, the phase locked feedback loop is not internally connected. That is, here there will be no connection in between these 4th pin and 5th pin. So it will not act as a PLL. Whenever you want to use it as a PLL, then you have to externally connect pin number 4 and 5. Then it will be used as a PLL. And if you want to use PLL in the frequency multiplications, then you can use a digital frequency meter or digital frequency divider in the feedback loop. That is, it will be connected in between the pins 5 and 4. Then you can easily calculate the number of frequencies. And coming to this pin number 8 and 9, here we are connecting the resistors R1 and C1 connected to pin number 8 and 9. And coming to here we are connecting a capacitor C2 in between the pins 7 and 10 across the resistance 3.6 kilo ohms to form the low pass filter. Center frequency of the VCO will be used as a free running frequency of PLL. That's why what I am telling is, while you are going to calculate the free running frequency of PLL, it's enough to calculate the center frequency of VCO. What is the center frequency of VCO? F naught is equal to 1.2 divided by 4 into R1 C1 hedges, and this R1 and C1 will be connected to the pins 8 and 9. By adjusting the values of R1 and C1, make that free running frequency F naught, which is nothing but the center frequency of PLL, will be exactly middle of the input frequency. And one more thing you have to remember in this case is the R1 is limited to a range, that is 2 kilo ohms to 20 kilo ohms. Always you have to choose the resistor R1 value in between 2 kilo ohms to 20 kilo ohms, and you can choose C1 should be any value, no problem about the value of C1. And coming to the capacitor C2 value, you can choose a large capacitance value. Why? Because to eliminate the possible oscillations of the VCO input voltage, which is nothing but the control voltage. So to eliminate the possible oscillations in the control voltage, you have to choose the large capacitance value for C2. And coming to the lock range and capture range, already we discussed about the lock range as well as capture range definitions while we are discussing about the block diagram of PLL. What is a lock range? Whenever the input frequency will be equal to the feedback frequency, then we may call it as the PLL is locked. The range of frequencies over which the PLL is maintained lock is called as lock range. And coming to the capture range, the range of frequencies over which PLL can acquire lock is called as capture range. And lock range frequencies and capture range frequencies values. That is FL is equal to plus or minus 8 F0 divided by V, where F0 is nothing but the center frequency or free running frequency, and V is nothing but plus VCC minus VCC, okay, which is nothing but V. And coming to the lock range, the lock range will be increases with the increase of applied control voltage at the VCO. Why I am telling, as if V is directly proportional to FL. So whenever the control voltage is increases, then the lock range will be increases, and whenever the supply voltages are increases, then the lock range will be decreases. Why? Because FL is inversely proportional to V. That's why the lock range is depends upon the control voltage, and also it will be depend upon the supply voltages. Okay, now coming to the capture range, FC is equal to plus or minus FL by 2 pi into 3.6 into 10 to the power of 3 into C2 whole to the power of 1 by 2. And coming to this case, the pin number 6 and pin number 7 are approximately equal, and that sixth pin will be used as a comparator reference input in frequency shift keying technique. And other applications of the comparator also you may use it as a reference input. And related output, it is always approximately equal to the reference output. And now coming to the phase detector, here if you are observing that we are applying the 3 inputs to the phase detector, and pin number 2 and input at pin number 3 are directly coupled, provided there will be no DC voltage difference between the 2 input signals. Then only we can directly couple those 2 inputs. Okay, and phase detector, other input of the phase detector is coming from the output of VCO. Diagram of IC 565 PLL, the pin number 5 and pin number 4 are not connected externally. Whenever you want to use it as a PLL, first you have to connect these 2 pins externally, then only it will be used as a PLL, and you can start the usage of this PLL. Derivation of lock range. This block diagram explains the derivation of lock range. Now, what is output of phase detector? Phase detector compares the input frequency and generates an output which is a function of phase difference between the 2 input signals. Here I am taking the output of phase detector will be equal to VE. VE will be taken as K phi into theta E minus pi by E, where theta E is nothing but the phase error. Now this phase detector output will be passing through the low pass filter, which removes the high frequency component present in the output of phase detector. Generally the phase detector output is a high DC voltage, and which will be amplified with the help of op-amp, and that will be applied as an input of VCO, which is nothing but the control voltage or error voltage. So VC will be taken as A into VE, which will be taken as A into K phi into theta E minus pi by 2, which is nothing but the control voltage which is applied at the input of VCO. So always we will be treated as control voltage will be used to generate the output frequency of VCO. So the output frequency of VCO is shifted from center frequency F0 to F0 plus kV into VC. So which is nothing but F is equal to F0 plus kV into Vc, okay, where f naught is nothing but free running frequency or center frequency, and kV is voltage to frequency conversion factor, and Vc is nothing but the applied control voltage at the input of VCO. And whenever PLL is locked, then what happened? F is equal to Fi. So when PLL is locked, F will be equal to Fi, and Fi will be equal to F naught plus kV into Vc. So whenever PLL is locked, now we can rewrite it as Fi minus F naught will be equal to kV into A into k phi into theta e minus pi by 2. From this, theta e minus pi by 2 will be equal to F phi minus F naught divided by kV into A into k phi, which is nothing but theta e minus pi by 2. Maximum output voltage magnitude of the phase detector is generated when theta e is equal to pi r 0 degrees. So what happened? VE max. So VE max will be represented as k phi into pi minus pi by 2, which is nothing but 2 pi minus pi, that is equal to pi by 2. So k phi into pi by 2. And at the same time, the maximum control voltage is generated as, which will be taken as VC max. VC max is equal to A into k phi into pi by 2. Okay na? Substitute the maximum values of Vc in this equation. Now this equation will be rewrite as, take it as equation number 1, and here the theta e will be equal to plus or minus pi or 0 degrees. So it will be rewrite as plus or minus. So substitute this Vc max in equation number 1. Now it will be rewrite as Fi is equal to F naught plus kV into Vc max is nothing but plus or minus A into k phi into pi by 2. So kV into A into k phi into pi by 2. Now the lock range will be taken as 2 into delta FL, which is nothing but kV into A into k phi into pi. Okay, so finally we will be get that lock range delta FL will be getting as kV into A into k phi into pi by 2. So this will be rewrite as Fi is equal to F naught plus or minus delta into FL. Generally the lock range will be represented as 2 into delta FL. Remember this. But delta FL is this. Whenever you multiplied with the 2, then this 2 will be cancelled. So delta FL is this, and 2 into delta FL will be equal to kV into A into k phi into pi. Okay, now what is the value of kV, and what is the value of k phi, and what is the value of A from the IC 565 PLL? The range is symmetrically located to free running frequency of VCO, and kV is equal to 8 F naught divided by V, and A is equal to 1.4, and k phi is equal to 1.4 by pi. Substitute all these values, then we can easily calculate the value of delta FL. Now coming to the calculation of delta FL, kV is equal to 8 F naught divided by V, where V is nothing but plus VCC minus of minus VCC, which is nothing but V. 8 F naught divided by V into, what is k phi? 1.4 divided by pi into 1.4 into pi divided by 2. And if you calculate this value, you will get it as plus or minus 7.8 F naught divided by V, which is nothing but the derivation of lock range, and which is delta FL.